So let's talk about the periodic table a little bit. We have what we call main group elements. This thing I call the S block, and this thing over here I call the P block, and this thing I call the D block, and we're missing the F block down at the bottom. And this periodic table is real nice. Notice it's different than that one over there. That one over there we ought to throw in the dumpster. Now we have regular numerals here, 3, 4, 5, 6, 7, 8th. 8th group, 7. And we might make use of these numbers here in a little bit. So you had a little bit of practice with naming some of these, being asked which one's an alkaline metal or alkali metal, which one's an alkaline earth metal. Either of those metals, alkali metals or alkaline earth metals, probably do what to the soil? Especially around here where there's like some standing water. What do you see on the edges? Yeah, you see this white, and you might say, oh, that's an alkaline pond. Yeah, that white. You can imagine a lot's probably sodium, since this is Natrona County. Noble gases, halogens, chalcogens, and that's about it. Alkali metals, they all form +1 cation. And in nature, that's how we find lithium. In nature, that's how we find sodium. These are all very active. Metals like to give up electrons. So here when we have lithium like this, kind of looks like vanilla beans or something. This had to have been made in the lab. And sodium metal, likewise, you put it in water, it reacts vigorously. So all these form +1 cations. How are you going to remember that? What do you see written right here? Number 1. Yeah, this tells you every metal in this column has 1 valence electron. Metals like to give up electrons. If that 1 valence metal goes away, you're going to get metals with this charge. So you don't necessarily have to memorize that all these are +1. You can look at the periodic table and figure out they're +1. All right, so that's got you warmed up. What number do you see above this column in the periodic table? 2. So what type of cation does beryllium form? Yeah, +2. And we like to put the number and then the charge. So every metal in this column has 2 valence electrons. Metals like to give up electrons. So this should remind you of lab. Calcium metal shavings were even that shape. All right, what number do you see above the halogens? That Roman numeral, which is 7. True or false? This is going to form a +7 cation. Good, I see some of you shaking your heads. Hopefully my grinning poker face gave you a heads up. What do non-metals like to do? What was that? Yeah, they like to hog electrons. They like to take electrons. So 8 is like a magic number. What is 7 minus 8? Right, so fluorine here becomes fluoride. Chlorine wants to be chloride. Bromine likes to be bromide. Iodide likes to be iodide. So that's one way to look at it. Another way to look at it is what I like to say, everything wants to be like a noble gas. The alkaline earth metals and the alkali metals do so by losing electrons, and they back up to the nearest noble gas. All these grab 1 more electron and then they become like a noble gas. So fluorine, if it gets 1 more electron, it comes like fluoride, or it becomes fluoride, and then it's like neon. Chlorine gets 1 more electron, comes like argon. So we can subtract 8 from the number here, and if we go 7 minus 8, we got the -1. Let's think about oxygen, my favorite atom. What's the charge on oxide? -2, absolutely. And we go 2 negative, that's how we like to write that. So notice I have to jump over 2 spots. Oxygen needs 2 more electrons to become like neon. And we could go 8's this magic thing. I see a 6 here. 6 minus 8 equals a -2. So that's how we can figure out all these charges. So what kind of ions do the noble gases form? Can I smile a lot and get a response? Before they were called the noble gases, they were called the inert gases. What does inert mean? Yeah, it doesn't react. All right, so the noble gases are noble because they have what we might say, a full electron shell. They have all the electrons they want. Their electron configuration is perfect. So they're not very reactive. So that was a bad question, asking you what type of ion. The answer is they don't like to form ions, Eric. And some of these heavier ones, chemists have now made compounds out of. But for years, nobody could make a compound out of those elements. In chemical reactions, atoms often lose or gain electrons to form charged particles called ions. We also want to understand ions because we can have ions from various sources like salts and solutions, and we can form new ionic substances. Positive ions are called cations. Negative ions are called anions. Hear that Freudian slip? The charge of an ion is shown in the upper right corner of the symbol. Ion charges are usually written with the magnitude of the charge first, followed by the sign of the charge. How many of you drive an old beater car? I used to, then I bought a car last June. Now I can't retire when I want. So car cancer is called rust, and that's when oxygen reacts with the iron in your fenders. Nowadays, a lot of your fenders might be plastic. And so when iron and oxygen combine, we get this thing we can call rust. That's a common name. We can also call it iron 3 oxide. So I'm jumping ahead into the next chapter a little bit. Things you're going to want to be able to do, but knowing these charges on cations and ions is fundamental to what we want to do. It's also fundamental to naming some things, fun things from our next chapter. Lithium's a metal. It wants to lose its electron. It only has one electron, what we say is in an outermost energy level. We call it a valence electron. How many electrons does lithium have to begin with? How many protons? 1, 3. The charge of an ion depends on how many electrons were gained or lost. So to apply that to what we've gone over today, magnesium in that second column can lose 2, become a +2. Sodium can lose 1, become +1. Oxygen can gain 2 and become oxide, -2 charge. Chlorine gains 1, and the number of protons is fixed. So as the electrons change, either gaining an excess, like a nonmetal, or being a metal and having an excess of protons to electrons, getting a positive charge, +1. And fluorine, Roman numeral 7, 7 minus 8 is -1. Or we see it's right next to neon and it only needs to jump over 1, so it needs 1 more electron. So we've already gone over this a little bit. The number associated with the letter A above each main group column in the periodic table, 1 through 8, gives the number of valence electrons. You just heard me say that a second ago. Valence electrons are in what we call an outer energy level. There must be lower energy levels in an atom. The key to predicting the charge acquired by an element is given by the position that element has in the periodic table relative to the noble gases. So I said the alkali metals and the alkaline earth metals back up by losing electrons to the nearest noble gas. Nonmetals gain electrons to become like the closest noble gas in number of electrons. And main group elements tend to form ions that have the same number of valence electrons as the nearest noble gas. So here we see all these put together. -1, -2, you can probably go -3, -4. Get over here, now we're to a metal with aluminum. So it's going to back up and lose 1, 2, and then 3 to become just like neon. And fortunately or unfortunately, transition metals form cations of various charges, so we don't make predictions. Now notice iron, I just wrote this word, or this name, iron 3 oxide. We had to tell the reader the charge on iron. We never say magnesium 2 oxide. If I say magnesium oxide, it's up to the reader to say, oh, magnesium oxide, that has that chemical formula. This thing here, the reader has to say, oh, I got iron with a 3+ charge. I got oxygen turned into oxide, it's got that -2 charge. And while we're here, I'll just tell you, things come together in such a way to be electrically neutral. So all the positive charge has to negate all the negative charge. And there's a hard way to do it, and then there's an easy way to do it. I'll show you the hard way first so you can impress your friends and family. Our subscripts give us the number. So there's the algebraic expression. If we can solve for x and y, we can figure out these subscripts. So I have an x there and a y there. And so what students are told to do, what's the least common multiple between 3 and 2? What is it? Not everybody shout it out at once. Least common multiple, but 6. Very good. All right. And if I go 3 goes into 6, how many times? Twice. And if I go 2 goes into 6, how many times? 3 times. Now if you plug this in here, 2 times a +3 summed with y = 3 times a -2. That indeed does sum up to 0. Now you can really impress your family and friends with this algebra. So there's this little mnemonic. When I get to that slide, I'll have to skip it since I explained it now to a certain extent. You can find that common multiple and do these substitutions real fast by taking that charge and using it as a subscript, using that charge and using it as a subscript. However, there are times when it breaks down. What about this thing? Why isn't there a 2 and 2 there? Yeah, we want the lowest whole number ratio, and a 2-to-2 ratio is really a 1-to-1 ratio. Or if I said, not everybody shouted out, everybody's scared and bashful. What's the least common multiple between 2 and 2? 2. 2 goes into 2 how many times? 1, yeah. We want to talk about isotopes. That last slide just said something like all atoms of a given element have the same number of protons, of course. That's the atomic number. That gives the identity. But the number of neutrons can vary. That's why we have carbon-14 and carbon-13, which we call isotopes. Different numbers of neutron give rise to different isotopes of an element. All elements have their own unique percent of natural abundance of isotopes. So neon, naturally occurring. That means what we find in nature, not what we make inside a nuclear reactor or something. 3 different types of isotopes. Neon 20, 10 protons, 10 neutrons. Neon 21, 10 protons and 11 neutrons. And neon 22, 10 protons and 12 neutrons. And we can see the majority of neon is neon 20. 9.25% is neon 21, and a small percent is neon 22. Here's how we like to depict isotopes. So I think a week ago I kind of went over this a little bit. This is all carbon because each one of these atoms has 6 protons in its nucleus. This also has 6 neutrons. So the mass number is the sum of neutrons and protons. We got our carbon-13 and carbon-14. And then, of course, the other way to depict isotopes is symbol of the element followed by the isotope we're talking about, like neon 20, neon 21. So if I look at this periodic table over there. I can't read it, it's too far away. Looking over there and I see chlorine, and we have 17 up here. And down here I see 35.453. Thank you so much. So according to this, it says we have some chlorine 35 and we have some chlorine 37. Thank you. So here's two isotopes. Let me make that look like a comma. So this is called the atomic weight, which is the weighted average of all the naturally occurring isotopes. So here's the isotopes and their mass, and here is the naturally occurring abundance. 75.77% is chlorine 35, 24.23 is chlorine 37. So the big question is, and what you want to learn today before we leave, is how to calculate an atomic weight. How to take a weighted average of these two things and sum them together. So what does 75.77% mean? That might mean if we had a 100-gram sample, how many grams, what's 75% of 100? Might mean something like that, right? That's what, if you got a 75% on your exam and there was 100 points possible, how many points did you get? You got 75 points, all right. So this is what percent means, so many out of 100, and that weighs, notice percents are kind of unitless. I drew that in there to help you understand. Let me make it, use the test analogy. If you got 75 on your 100-point exam, that means you got 75 points out of 100. So that's going to find 75% of that number. All right, now we want to find 24.23%. So that means per 100 of chlorine 37, and chlorine 37 has a mass of 36.97 atomic mass units. So I brought my calculator in. Hopefully you brought yours. You can always use the calculator on your phone now, just not on the exam. And you should get something close to this. Doesn't exactly round to that periodic table over there. I've never trusted that periodic table. So this is how you find a weighted average. We found 75% of this number, 75.77 to be exact, and 24.23% of this number, and we sum those together. Now let me round this appropriately. Everybody able to get the same number? Good. And maybe you do this when you go to a store, right? If they say 50% off, you divide by 2, right? What's 50% off of $300? I'm not taking you shopping. You need to work for the store. All right, let's try this. 50, divide 100, multiply 300. There, I found 50% of $300. Gallium has two naturally occurring isotopes, gallium-69 with a mass of 68.9256 atomic mass units and a natural abundance of 60.11%, and gallium-71 with a mass of 70.9247 atomic mass units and a natural abundance of 39.89%. Calculate the atomic mass of gallium. I'm going to do it on my calculator. I really got to focus. I think I got something reasonable. Looks like I only know my percentages to 4 digits. If I could see that periodic table over there, it should be close. 723, very good. All right, so what do you think I did? You want to convert the percent natural abundance into a decimal by dividing by 100. 60.11% means per 100, divide that. There's our decimal fraction. Do the same thing with our 39.89% divided by 100. And then what? So this is a step-by-step description of what goes on. So here's my 60.11%. I'm going to find 60.11% of 68.9256, AMUs. And here's my 39%. Divide that by 100, you get this fraction, and I'm going to multiply this by, and that's going to spit out that number there. Now, of course, on your calculator, if you don't make any fat finger errors, you can go 60.11 divided by 100 multiplied by this number plus 39.89 divided by 100 multiplied by this number and hit enter, and you should get this number right here. Or if you trust yourself, instead of going 60.11 divided by 100, you just do that in your head by moving the decimal over, and you go 0.6011 times this number. Take your 39.89% and do the same thing. Just go 0.3989 times 70, and that gets you there. Any questions on how to find a weighted average? So isotopes in the environment. The nuclei of some isotopes in a given element are not stable. That sometimes makes them radioactive. These atoms emit a few energetic subatomic particles from their nuclei and change into different isotopes of different elements. The emitted subatomic particles are called nuclear radiation. The isotopes that emit them are termed radioactive. Uranium 235 and 238 are both radioactive, and they eventually turn into lead 208. Now those things are a bit harmful. Here's some harmful ones. Long half-life, but not all isotopes are harmful. Here's this technetium. It's right there in between molybdenum and ruthenium, and it's used a lot in nuclear medicine. And maybe you've heard of a PET scan, positron emission topography. All right, that will do it.